Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 6 Spectrum. We will be discussing the topic Electromagnetic Spectrum and solve questions from Exercise 6B. Are you ready for the session? Let's begin. We know that when white light passes through a glass prism, it spreads into 7 different colors. So, we have discussed the term spectrum. Spectrum is a band of colors: violet, indigo, blue, green, yellow, orange, red. These colors are visible to our eyes. So, when this experiment is performed, that is taking a glass prism, when white light is passed, what happens? The white light splits into 7 different colors. So, are these the only things that are present in white light? White light contains other radiations too. So, this part, that is from violet to red, is called the visible spectrum, that is visible to the eyes. Okay, and it also contains radiations and waves which are not visible to the eyes. These are called the invisible spectrum. Okay, so we can define the invisible spectrum. The part of spectrum beyond the red extreme and the violet extreme is called the invisible spectrum. So here you can see we have the red color and here we have the violet color. Okay, you can see the wavelengths. So the wavelengths above and below the visible region. Okay, there are some other radiations. These are called the electromagnetic radiations. Okay, visible is just one part of the electromagnetic radiations. Visible radiation is one such electromagnetic radiation. Above the wavelengths of visible light and below the wavelengths of visible light, there are other radiations. All these together we call the electromagnetic radiations. And except the visible light, all other radiation are invisible. We are not able to see them. So they are together called the invisible spectrum. Now we have studied about the visible light. We have studied VIBGYOR. The maximum wavelength will be for red light, lambda maximum, and minimum is for violet. So, if the wavelength is greater than the red light in the electromagnetic spectrum, you have 3 other radiations with wavelength greater than the wavelength of visible light. They are infrared radiations, microwaves, and then radio waves. So, maximum wavelength is for radio waves. Lambda max is for radio waves. Now, if the wavelength is less than the wavelength of violet color, that is wavelength less than that in the visible light, you have 3 other radiations: ultraviolet radiations, X-rays and gamma rays. So, here we are given the visible light in nanometers, okay, which is a smaller unit of length. Millimeters are used to give the wavelength of radio waves, microwaves and infrared waves. Okay. Smaller wavelength we have for ultraviolet, X-rays and gamma rays. So, minimum wavelength is for gamma rays. We know wavelength and frequency. What is the relation? When wavelength increases, frequency decreases. Okay, maximum wavelength with minimum frequency it will be having. Okay, now the complete electromagnetic spectrum in increasing order of the wavelength is given below, which will be having the maximum. Maximum will be for radio waves. So, starting gamma rays, then X-rays, ultraviolet rays, visible light, infrared radiation, microwaves and radio waves. So, if you are taking the increasing order of frequency, is taken, then first we will be having the radio waves. Radio waves. Okay, maximum wavelength, minimum frequency. Second, you will be having microwaves. Third, you will have infrared radiation, IR. Fourth is the same, that is visible light. Visible light. Fifth, you will have ultraviolet radiations, UV radiations. Then sixth, you will have X-rays. And seventh will be gamma rays. So, on both sides of visible light, in the electromagnetic spectrum, we have invisible spectrum, which includes the radio waves, microwaves, infrared waves and ultraviolet, X-rays and gamma rays. Okay, speed, frequency and wavelength of electromagnetic waves. So we have said that the wavelength will be in the decreasing order. Here we have radio, micro, infrared, visible, ultraviolet, X-rays and gamma rays. So we have understood that the wavelengths of the waves will be different. Different radiations will be having different wavelengths. Okay, so depending on that, the frequency will also be different. There is a relation between frequency and wavelength. What is the relation? We have speed of light. Okay, so remember one thing, the speed of light in vacuum. For all these radiation, the speed of light will be 3 into 10 raised to 8 meter per second. So what is the relation? Speed of light C is equal to lambda into F. Speed of light is equal to wavelength into frequency. So this is the relation. If frequency and speed of light is known, you can find wavelength. Lambda will be equal to C by F. So this is a case in vacuum or air. Okay. Then if you want to find frequency, then frequency will be speed of light divided by wavelength lambda. So these are the relation to find frequency and the wavelength when speed of light is known and one other quantity is known. Clear? So we studied about the visible light. We have said there is no sharp boundaries. After red, can you see a boundary between red and orange? No, right? Between orange and yellow, there is no sharp boundary. Is it like this? Till here red color, after that orange, after that yellow, then green, then blue, then indigo, then violet. No, right? So there is an overlapping. Red overlaps with orange. Orange overlaps with yellow. Yellow overlaps with green. Green overlaps with blue. Blue overlaps with indigo. And indigo overlaps with violet. Same is the case when the complete electromagnetic spectrum is considered. So there is no boundaries between radio waves and microwaves. No boundary between the microwaves and infrared, then infrared and visible, visible and ultraviolet, ultraviolet and X-rays. There is no strict boundaries, X-rays and gamma rays. Okay, so this is a very important point. There is no sharp boundary of wavelength or frequency between two successive electromagnetic waves. They overlap to a great extent. So, like the rays in a visible light overlap, all other invisible spectrum, all other waves in the invisible spectrum also overlap. Okay. Now, the infrared, you can see that just after the red color, you have the infrared radiations. And just before the violet, you have the ultraviolet radiations. Okay. The infrared spectrum is a part of the spectrum just beyond the red end, while the ultraviolet spectrum is a part of spectrum just before the violet end. You can see this clearly, right? Just before violet you have ultraviolet, just after red you have infrared. So close to the visible light, on one side you have the infrared radiation and on the other side you have ultraviolet radiations. Okay, you should have an idea about the value of wavelength of the different radiations, because sometimes you may get problems like you have to find the wavelength and predict which type of radiation it is. Okay, so here the wavelength in nanometers is given. What is nanometers? We know 1 meter is equal to 10 raised to 9 nanometer, or 1 nanometer is 10 raised to minus 9 meter. Okay, wavelength will either be given in nanometer or we have another unit which is angstrom. Okay, what is angstrom? 1 meter will be equal to 10 raised to 10 angstrom, or 1 angstrom is equal to 10 raised to minus 10 meters. Okay. Now, we have 1 meter is equal to 10 raised to 9 nanometer and 1 meter is equal to 10 raised to 10 angstrom, which means 10 raised to 9 nanometer is equal to 10 raised to 10 angstrom. Okay. So, 1 nanometer will be equal to 10 raised to 10 divided by 10 raised to 9 angstrom. That is equal to 10 angstrom. Okay. So, 1 nanometer, interconversion is very important. 1 nanometer will be 10 angstrom, or 1 angstrom will be equal to 10 raised to minus 1 nanometer, which is 0.1 nanometers. Okay, 1 angstrom is equal to 0.1 nanometer. So first for gamma rays. For gamma rays, the wavelength is below 0.01 nanometer. What is 0.01 nanometer? 0.01 nanometer. If you need it in angstrom, how to convert in angstrom? We have 1 angstrom is equal to 0.1 nanometer. Okay, so we are given 1 nanometer will be is equal to 10 angstrom, which means 0.01 nanometer will be 0.01 into 10 angstrom, which is 0.1 angstrom. Okay, so below 0.1 angstrom will be the wavelength of gamma rays. Okay, then X-rays. X-rays, it is between 0.01 nanometer and 10 nanometer, or 0.1 angstrom to 100 angstrom. Next comes the ultraviolet. Ultraviolet, we know, just close to the visible light we have ultraviolet radiations. So for ultraviolet radiation, it is from 10 to 400. 400, we know 400, there the visible light starts. That is, the violet color starts at 400, which means 100 angstrom to 4000 angstrom is ultraviolet radiation. Then comes the visible light. Visible light we have studied, the wavelength ranges we have studied. So 400 nanometer to 800 nanometer is visible light, which means 4000 angstrom to 8000 angstrom we have visible light. Then comes the infrared waves. Infrared waves, just after the red color you have infrared waves. Okay, it is also close to the visible light. 800 to 10 raised to 6 nanometer. That is infrared waves. Then the microwaves. Now the wavelength you can see is increasing. We have started with below 0.01. Here it is 10 raised to 6. The power is 10 raised to 6. So microwaves 10 raised to 6 to 10 raised to 9. And then comes the radio waves, which is above 10 raised to 9. Okay. And the minimum frequency will be for radio waves. Maximum frequency will be for gamma rays. Clear? We have to study some common properties of electromagnetic spectrum. That is, we have studied 7 different waves. What is common in them? What are the common properties in them? First one is, electromagnetic waves do not require any material medium for their propagation. We know that sound waves need a material medium for propagation. That is either in air, water, or in solids. We know that sound waves can travel at a higher speed in solids. Then comes liquid and then gases. Okay, so when you take the electromagnetic waves, they actually don't require any medium for their propagation. This is the first point. Next, they all travel with the same speed in vacuum and air and with different speeds in different mediums. So we have said this point before, the speed of light 3 into 10 raised to 8 meter per second. So all these radiations which is present in light, that is either in the invisible spectrum or in the visible spectrum, will be traveling with the same speed, that is 3 into 10 raised to 8 meter per second in air or in vacuum. This is not the case in case of other mediums, like if you are taking water or solid mediums, this is not the case. There will be difference. Okay, different radiation will be having different speeds. Third point, they exhibit the properties of reflection and refractions. So we have studied what reflection and refraction are. Laws of reflection and refraction we have studied. What is first law of reflection? Incident ray, reflected ray, normal. At the point of incident, all lie on the same plane. Incident angle and the reflected angle are equal. Then we have discussed Snell's law when we came to refraction. Sine of angle of incident divided by sine of angle of refraction will be giving you the refractive index. Okay, so all these are obeyed by the electromagnetic radiation as well. So when refraction happens, what is refraction? Refraction is the bending of light when light travels from one medium to other. So when this happens, we know that the speed of light can change because medium is changing. Speed of light will change. Wavelength will change, but the frequency will remain constant. Fourth point, these waves are not detected by electric and magnetic fields. So we know that these are electromagnetic waves. Okay, they show electric and magnetic properties. So when you take the electric field and magnetic field, they will be perpendicular to each other, and the direction of propagation of the electromagnetic waves will be perpendicular to both the direction of electric field and the direction of magnetic field. Okay. These electromagnetic waves propagation is not they do not interact with the electric or magnetic field, or they are not detected by the electric and magnetic field. Okay, so this is the fourth point. Fifth point, these waves are transverse in nature. We have studied about two types of waves. One is transverse waves and the second is longitudinal waves. Sound waves are longitudinal in nature. They will be in this way. Okay. Compression, rarefaction type, you will be having sound waves. So when you come to light waves, they are transverse in nature. This is how the waves looks like. Okay. So here you will be having crust and this is trough. Crust, trough, crust, trough. Okay. Now to get the wavelength, what is wavelength? Wavelength, you start from one end, that is one crust, to the other crust. This distance we call the wavelength. All this we have discussed before. The maximum displacement possible is the amplitude. Okay. So here you have the wavelength. When you take troughs, this is also, okay, that is between two consecutive troughs, the distance will be the wavelength. Half of wavelength you will be getting, that is when you take the distance between a crust and a trough, you will be getting lambda by 2, half of the wavelength. Okay, so these are the 5 important points, that is properties shown by all the electromagnetic radiations. Now we will be discussing the source, properties and uses of ultraviolet radiation. So what are ultraviolet radiation? We know just below the violet light you have a radiation which we call the ultraviolet radiation, whose wavelength is less than that of visible light and the frequency will be higher. So electromagnetic radiation of wavelength from 100 angstrom to 400 angstrom or 10 nanometer to 400 nanometer are called the ultraviolet radiations. Okay, so these are also called UV rays. Ultraviolet radiations are UV rays. So where do we get this ultraviolet radiation? So the detection and source is not included in your syllabus. You just need to study the properties and uses of ultraviolet and infrared radiation. So source of ultraviolet radiation, they are obtained in radioactive emissions. So radioactive reactions, so we will be studying radioactivity later. So in this radioactive emission, the radiations that is obtained is the ultraviolet radiations. Okay, when the nuclei of a radioactive atom pass from an excited state. So when it is in the excited state and when it passes from an excited state to the ground state, what happens is radiations are released out and these radiations are the ultraviolet radiation. Also in cosmic reactions or cosmic radiations, these ultraviolet radiations are present. Now we'll discuss the important properties of ultraviolet radiation. We have discussed some common properties of all electromagnetic radiations. First one, ultraviolet radiation can pass through quartz. So when you take glass, glass absorbs these ultraviolet radiation. We know that when you take a glass prism, the white light, what happens? It splits into the 7 different colors. We are getting only the visible thing. Okay. The ultraviolet radiations present in the white light will pass through the quartz prism, but if you are using a glass prism, it will be absorbed. So this is how a quartz prism looks like. So to get the ultraviolet spectrum, you can use a quartz prisms. So this is the reason why you will be using, when you take an ultraviolet bulb, in that the envelope will be made up of quartz instead of glass. Why? Because glass will absorb the radiation, ultraviolet radiation. Then the UV rays will not be obtained. Second point, these radiations travels in a straight line with a speed of 3 into 10 raised to 8 meter per second in air or vacuum. This point we have already discussed before. This is a common point to all the electromagnetic radiation. They will be having the speed of light to be 3 into 10 raised to 8 meter per second. Now the third point, they are usually scattered by dust particles present in the Earth's atmosphere. We have studied scattering. What is scattering? So when a light ray, it strikes some dust particle, it will be getting shattered. Okay, the same thing will happen with the ultraviolet radiations too. Okay, next they obey laws of reflection and refraction. Reflection is just the bouncing back of light and refraction is the bending of light when light travels from one medium to other. So ultraviolet radiation also obeys these laws of reflection and refraction. Okay. Next, they strongly affect a photographic plate. A photographic plate will be containing light sensitive materials. For example, silver halides or silver bromide. Okay. And they will be interacting as they are chemically more active than visible light. When you compare visible light and ultraviolet radiation, they are more active compared to visible light. So when you take a photographic plate which contains these silver bromides and or other silver halides, these ultraviolet radiation will be affecting it more strongly. Next point, they produce fluorescence on striking a zinc sulfide screen. So you know what is fluorescence? So at night time you will be seeing some glittering effects due to the fluorescence. So these ultraviolet radiation can produce fluorescence when it strikes a zinc sulfide screen. Okay, so these are the important properties of ultraviolet radiations or UV rays. Now, where are these ultraviolet radiations used? Okay, first, ultraviolet radiation are used for the following purposes. First is for sterilizing air, surgical equipments, etc. So, for cleaning purposes and all, when you have the surgical instruments, surgical equipments to clean, you can sterilize it, you can use the ultraviolet radiations. Next, the second point, for detecting the purity of gems, eggs, ghee, etc. Okay, so these things, if it contains impurities, it can be detected using the ultraviolet radiations. Next, in producing vitamin D in food of plants and animals. We know sunlight is used by plants. Why? To prepare food. We know the process of photosynthesis in detail. From small classes we are studying. What happens in photosynthesis? Green plants, they absorb sunlight using carbon dioxide and water, and chlorophyll, they prepare food. Okay, for this, when you take sunlight, the sunlight contains infrared radiation, visible light and different ultraviolet radiation. So, these ultraviolet radiations are used to activate the vitamin D. Okay, now what are the important properties of infrared radiations? First, they travel in straight lines like light with a speed equal to 3 into 10 raised to 8 meter per second. So, like all other electromagnetic radiations, here also the speed of light in air or vacuum will be 3 into 10 raised to 8 meter per second. Second point, they obey laws of reflection and refraction. So, we have studied ultraviolet radiations also obey the laws of reflection and refraction. So, these are powerful radiations. So, we have studied about parabolic mirrors, convex and concave mirrors. When parallel beam of lights are passed, what happens? It gets focused at a point. We know this. So, sunlight can be focused in this way. So, here when you take infrared source of light and pass through parabolic mirrors, what happens is parallel beam of light is obtained. So, if you are using a convex lens, again when you use a convex lens and an infrared radiations to this is passed, it gets focused at a point. For example, if you are keeping a paper in front of the lens and ultraviolet radiations are passed from one side, what happens is all that gets focused to one point and the paper will start burning. Okay, so these are powerful radiations. Next, they do not affect the ordinary photographic films. So, if you are using specially treated photographic films, it will be affected. That is the photographic films, we have spoke about it in the radiations. They contain halides, that is silver halides or like silver bromide and all. Okay, so these radiations are not that powerful to affect the ordinary photographic film, but specially treated photographic films will be affected by the infrared radiations. Okay, next, they are absorbed by glass. We have said the infrared radiations and also we have discussed the ultraviolet radiation, both will be absorbed by glass. Okay, but they can easily pass through the rock salt. When rock salt is used, they can pass through rock salt, but they will be absorbed by glass. Whereas in the case of visible light, they are not absorbed. They get split into the different colors. Next, they are detected by their heating property using a blackened bulb thermometer or a thermophile. So, these radiations are heating. Okay, heating properties can be measured using the thermophile. This is how a thermophile looks like, or the blackened bulb thermometer can be used for this purpose. 6. They are scattered less by the Earth's atmosphere because of their long wavelength. We know that what is happening to wavelength when we go from gamma rays to radio waves, the wavelength is increasing, right? So, infrared radiation will be having wavelength, that is an increased wavelength. That is the scattering is directly proportional to, or scattering is proportional to 1 by lambda raised to 4. Okay, which means when wavelength increases, what happens? The scattering will be decreasing. Okay, so they do not get scattered easily because of their higher wavelength. Okay, so they can pass even through the mist and fogs. They don't get scattered. What is the reason? Because scattering is inversely proportional to the fourth power of wavelength. When wavelength increases, what is happening? Scattering will decrease. Okay, due to their long wavelength, they can be visible in fogs and in mist. Next, the greenhouse gases such as carbon dioxide present in the Earth's atmosphere absorbs the low energy infrared radiations and keep the Earth's surface warm. We know that energy, wavelength energy relation, energy will be equal to h into frequency, where h is a Planck's constant, which will be learning in higher classes. Okay, so depending on frequency, energy also changes. When frequency increases, energy will increase. Okay, so these radiations, when you take the case of these radiation, we have said they are having higher wavelength. Higher wavelength means the frequency will be low. Therefore, these radiation will be low energy infrared radiations. Okay, so these low energy infrared radiations, the greenhouse gases like carbon dioxide, when taken, they will be present in the Earth's atmosphere. That is present in Earth's atmosphere can absorb these low energy infrared radiations. Okay. Next, the important uses of infrared radiations. Infrared radiations are used for the following purposes. First one, used by doctors for therapeutic purposes. We know this infrared radiation will be used in medicines to detect or to diagnose stem cells, then for diagnosing cancers. For all these purposes, doctors will be using the infrared radiation. Next, they are used in photography at night and also in mist and fog. Here, this we have discussed. Which property is useful? Because scattering is inversely proportional to the fourth power of wavelength. So, wavelength is large, scattered. That is, the light does not get scattered easily. They can penetrate through the fog and mist. Infrared lamps are used in dark rooms for developing photographs. So, visibility is higher. They do not get easily scattered. Okay, so this is the reason they are used as signals during what? The same reason they can penetrate easily. Next, they are used in remote control of televisions and other gadgets. You might have seen these infrared radiations in the remote controllers because they can penetrate easily. Okay, they do not get scattered in any medium. They can penetrate easily. Now, let us solve numericals from exercise 6B. Question 1 of exercise 6B. An electromagnetic wave has a frequency of 500 megahertz and a wavelength of 60 centimeter. Calculate the speed of the wave, then name the medium through which it is traveling. So, first we are given the frequency. Frequency F is equal to 500 megahertz. Mega means 10 raised to 6 is the power, which is equal to 500 into 10 raised to 6 hertz. And a wavelength of 60 centimeter. Wavelength is given in centimeter. Wavelength lambda is equal to 60 centimeter. We know 1 meter is 100 centimeter, which means 1 centimeter will be 1 by 100 meter equal to 10 raised to minus 2 meter. So, 60 centimeter will be equal to 60 into 10 raised to minus 2 meters. Okay. So, this is 60 into 10 raised to minus 2 meters. Now, we have to find the speed of wave. So, we have speed is equal to frequency into wavelength. Now, put the values. Frequency 500 into 10 raised to 6, then wavelength 60 into 10 raised to minus 2, which is equal to 5 into 6 is 30, 2 zeros from here and 1 zero from here, into 10 raised to 6, the power is minus 2, okay, which is equal to 3 into 10 raised to 1, 2, 3, 4, 4 zeros into here 6 minus 2 is 4, 10 raised to 4, which is equal to 3 into 10 raised to 8, and the unit of speed is meter per second. 3 into 10 raised to 8 meter per second is the speed of light in air. Okay. So here the second part of the question, calculate the speed of the wave, is the first part. We got 3 into 10 raised to 8 meter per second. Now name the medium through which it is traveling. We know the speed of light in air or vacuum is 3 into 10 raised to 8 meter per second, which we represent by C. So here the medium is air or vacuum. Okay, question 2 of exercise 6b. The wavelength of X-rays is 0.01 angstrom. Calculate its frequency. So here we are given the wavelength lambda is equal to 0.01 angstrom. We know 1 angstrom is 10 raised to minus 10 meters. So 0.01 angstrom will be equal to 0.01 into 10 raised to minus 10 meters. Okay. Next, we are to find the frequency. What is the speed of wave? So here we know the medium. We are assuming the medium is air, and we can assumption speed of wave is equal to 3 into 10 raised to 8 meter per second. Okay, we can find the frequency. So we have frequency will then be equal to speed divided by wavelength, which is equal to speed 3 into 10 raised to 8 divided by the 0.01 into 10 raised to minus 10 meter can be written as 1 into 10 raised to minus 12 meters. Okay, that is 10 raised to minus 12 equal to 3 into 10 raised to 8 into 10 raised to 12. So from the denominator 10 raised to minus 12, when taken to the numerator, it becomes 10 raised to plus 12. This is equal to 3 into 10 raised to 8 plus 12, which is 3 into 10 raised to 20. So frequency unit is hertz. Therefore, the frequency of the X-rays is 3 into 10 raised to 20 hertz. So here we are assuming the medium is air and take the speed of wave as 3 into 10 raised to 8 meter per second. That's all for today. In today's class, we have discussed about the electromagnetic spectrum. We have studied the common properties and uses of ultraviolet and infrared radiation also we have discussed today. Also, we have solved 2 problems from this session. Hope you all enjoyed this. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai, par best hai. Thank you.